Okay, so we can start. So yesterday we completed a discussion on causality, and later today or latest tomorrow morning, I'll share notes with the class registered people, and also maybe a problem set. So today we start on a completely new subject. It is not new to you, of course, which is black holes. And you will see quite repeatedly applications of the things we have been doing since the beginning, including our study of geodesics, of isometries, and of causality issues, domains of dependence, things like that. You'll also see some formulae which you already know, but we'll go through them because if we need them. So let me start by writing the Schwarzschild solution from 1916, I think. And so this is a solution to the equation R mu nu equals 0. Surely one of the most beautiful equations in physics, because it partially constrains the curvature tensor of space-time, but not fully, so leaving the possibility that there could be many solutions. It's a set of coupled nonlinear partial differential equations. One could of course argue that all classical physics is nothing but coupled partial nonlinear differential equations, but certainly this is very nonlinear and very non-trivial. And in a way, it's remarkable that Schwarzschild could himself find a solution so fast after Einstein's theory was proposed. So we'll write that, and then we'll talk a little about its symmetries, and then we'll prove Birkhoff's theorem, which is that under conditions of spherical symmetry, this is the unique solution to these equations. There's also a corollary due to Israel, which says that if the solution is static and asymptotically flat, then again this is the unique solution. So you can even arrive at it without assuming spherically symmetric, if you assume just static and asymptotically flat. So we have to write the metric in some coordinate system, and the way it's found is to write this. T squared plus the same thing and the spherical symmetry, so it is clearly static, time independent. There's none of the coefficients depends on time. Immediately we see that del by del t is a Killing vector. And it's of course spherically symmetric, that we see from the fact that it doesn't depend on, the coefficients don't depend on theta and phi, and the last term is just the metric on a sphere. So now for this discussion, I've always been a little conflicted whether to talk about 4 dimensions or d dimensions, but I think for a while we can keep it d dimensions. Yes?
There is RH by R whole square in the first term.
Oh, sorry. Yeah, thank you. That keeps happening when one writes on the board. Yeah, absolutely. This is what I wanted to write. No, it's not square. So I don't know what I'm doing. I think I'm a little drowsy today. It's just that. Yeah. Okay. So let me just pretend that we are in d dimensions, but I am nervous that I may stumble soon and say something that's not true in d dimensions but only in 4 dimensions. So let's just see what happens. Okay, so the idea is that this is very much like the solution for the electrostatic field of a charge distribution. And there what you do is that you solve Maxwell's equations, but you just have a charge distribution of total charge Q, and then you want to know what is the field here. So the equations you solve are actually vacuum equations. So the equations for the electromagnetic field in a vacuum. But even though there's a vacuum in the area where the equation is true, there is something in the middle which is giving you that field. Okay, so it's very much like that. And here the picture is that there is a matter distribution, and it's assumed to be spherical and up to radius Rm, which we'll call the matter radius. And then this solution has different physics depending on whether Rh, which is an integration constant, is greater than or less than Rm. So for Rh greater than, Rm greater than Rh, this describes the metric outside any spherically symmetric body. But the R of the metric, of course, has to be outside that body. We have to be in the vacuum, which is outside the matter distribution. If R is less than Rm, you're simply not supposed to use this solution. Okay, because in that case, R mu nu is not going to be 0, it's going to be the stress tensor of that matter distribution. So it's valid only for R greater than Rm. Physically speaking, you can look at the solution, but you're not supposed. If Rm is really the matter distribution, then the solution physically is valid only for R greater than that. Now, an interesting fact, as far as I understand history, is that right up until the 1970s, which is when I did my PhD, it was thought that this is the application of that metric. End of the discussion. The next question you can ask is, very good, what is Rh in terms of physical properties of the body, and we can fix that, which we'll do in a moment. But it was not thought that there's any significance to any other regime other than Rm being greater than Rh, and then the place where you evaluate this metric always being outside Rm. So you can draw Rh completely fictitious surface, Rm a genuine surface filled with matter, and R the observer outside Rm. There's never any question what goes on there, because at least you can't take this solution there. So it's a very practical solution for physical objects, and then to understand what it means, we simply compare with Newtonian. You know all this, I'm just going over a little bit of this. Newtonian physics. At large R, far away from this body. So the expectation is that at large distances, this general relativity reduces to Newtonian physics. So what you do is you write GTT is equal to minus 1 plus HTT. And actually maybe I like it better to write it, well, okay, we can write this here. This is GTT of Minkowski, and I add a fluctuation, HTT. And then HTT obviously is just another name for RH upon R. And then in the limit of large R, one can show, and I'm not going to do that here, that HTT is just twice of phi, where phi is the Newtonian potential. and this is therefore equal to 2 gm, Newtonian potential of a massive body. Of mass m. And is the potential at a distance r from the center of that body. And so therefore 2 phi is 2 gm by r, that's htt, and that fixes all this, implies that rh is 2 gm. And so we have our beloved Schwarzschild solution with rh equals 2 gm. Okay. Good. And one can also verify that the geodesic equation for a particle in the weak field approximation at large r reduces to the equation of motion of a particle in a Newtonian potential. And of course, it's very beautiful, and you all know this, that in the Newtonian picture, there's a potential energy, and the particle follows the trajectory given by basically Newton's equation. But in general relativity, there is no potential or force at all. There's just a space-time. It replaces the force. It's not in additional to the gravitational force. It's actually the more correct way of thinking of the gravitational force, and the particle falls freely in that space-time. It's a free particle. But what's free in a curved space-time looks accelerating from a classical or non-relativistic perspective, and that's why a particle accelerates towards the center of a massive object. Okay. Now, of course, this solution reduces to Minkowski when m is 0, so when there's nothing. But of course, when m is not 0, it's quite different. In particular, so it has, okay, we'll talk about the symmetries in a moment. Before that, let me say that some people, of course, considered the possibility that Rm is less than Rh, in which case that picture looks completely different. So here you have the actual matter distribution, but here around it you have some surface which is nothing but 2 gm. It's just a parameter that's given by some parameter of the solution, and then we are outside here as always. So in this case, we can actually think of crossing Rh without reaching the matter distribution, and so whatever we find here should be a valid solution of Einstein equation and should have some physics associated to it. But as you know, that physics is a little complicated, and we'll unravel it slowly. So when I said that until the 1970s it was thought that this is not physical, not everyone thought that. Certainly Oppenheimer and Snyder considered the possibility of things collapsing and forming this kind of object, which is a black hole. And Penrose had studied it, and even Hawking later studied it. But there was a small community, growing but small, even in the 70s. And I would say the large body of physics, the large physics community, including the particle physics community, didn't take it very seriously. So I think unless you were in some place where general relativity was very big, there were some isolated universities where it was very big. Chicago is one of them, of course, people like Wald and so on. Of course, in the UK there was Cambridge and Oxford. But it had not penetrated, let us say, many universities, even this whole subject. And people were very skeptical. You can look at Weinberg's textbook on general relativity in that period, and it has literally nothing except the statement that probably this doesn't make sense, but that one makes sense. Okay, so now we are going to study symmetries and geodesics. For this solution. So one statement is that the solution has some of the symmetries of Minkowski spacetime. Obviously, it doesn't have the translational symmetry because there's an r coordinate in the solution, and therefore there's a preferred place r equals 0. Of course, Minkowski spacetime also can be written in polar coordinates where there's a preferred place r equals 0, but this one certainly has characteristics at r equals 0, which suggests that it's not just a bad choice of coordinates there. In fact, it's something serious is happening at r equals 0, unlike Minkowski, where we know how to eliminate that problem by just going to Cartesian coordinates. Okay, so one, of course, because it's static, so obviously we have t going to t plus any constant, and therefore d by dt is the killing vector. Okay. Secondly, because it has spherical symmetry, so it has 3 rotations. And any of them, for example, the z rotation can be written as the killing vector x del y minus y del x. I'm using the notation del y means del by del y. So like that, and then cyclically you'll get all the symmetries. Okay. Good. And it will be convenient to write these in terms of angles. Okay. Now we have shown previously, if u mu is tangent to a geodesic, and v is a killing vector, sorry, w, I prefer, then g mu nu, u mu w nu, which is the same as the dot product u with w, is conserved along the geodesic. And such things are very important because in non-relativistic or in flat space or flat space-time, we are used to saying that something is conserved in time or is constant in space, but we don't have those the ability to say those things in GR because we can change coordinates and something may look constant in time, but there are other coordinates where it doesn't look constant in time. So these are the sort of true invariant statements. But of course, you can just imagine, like just to get a intuition for this, that if u mu is time-like, then it's really 1, 0, 0, 0. And if this is Minkowski metric, it just means the 0 component of w is constant in time. So it's not so surprising, but this is the correct formal way to write it. Okay. Moreover, if u is the tangent to the geodesic, so we'll now assume the geodesic is either time-like or null, as we mostly do. And p mu, the for momentum, is mass of a particle. So for a particle of mass small m, the for momentum is proportional to the tangent vector, which is the for velocity. So this is the relativistic version of p equals mv. And then u dot u is -1 for time-like and is equal to 0 for null. And of course that gives you the corresponding equation on p, which says that p squared for vector is either -m squared or it's 0 for a massless particle. Good. Okay, so now let's look at the conserved, so let's consider conserved quantities. We'll consider several of them, but we'll start with actually we'll consider conserved quantities associated to the killing symmetry, which basically is p mu. So what am I saying here? Sorry, I said that wrong. We are considering this dot product p mu v nu, where this is a Killing vector. And p mu is just a scaled version of u. It is the tangent vector to a geodesic, but it has a factor of m built into it. So by the theorem we had, this is conserved. So whenever we calculate it for any particular Killing vector v, we'll get a conserved quantity, and then it's up to us to give that quantity some name. So, for example, if we choose, so we'll take a few examples. So let's take v mu to be just the Killing vector I already wrote down. Now I'm going to do 4 dimensions, just d by dt. So the first component is 1. So then that equation just says that g00 v p0 is conserved. And it's reasonable to call this thing the conserved energy, because in special relativity that's certainly true. Okay, notice that g00 in special relativity is -1, so this becomes p lower 0, and that's supposed to be the energy. So if we write this out, this equation, then g00 in the Schwarzschild metric is that, and then p is m times d, p0 is dt by d tau. We can think of tau as the affine parameter along the geodesic, and this is equal to E. So this is one of the equations we get from that conservation law. And yeah, so we see that it's a little non-trivial given that this varies with R. Okay, now we repeat the same thing for other Killing vectors, and the Killing vector that we would like to use among the 3 rotational ones is d by d phi, because that's simpler, the simplest. The others are written in terms of both theta and phi, but this is only d by d phi, so it's easy. This is always also why in quantum physics we quantize along the z-axis, because this is the rotation around the z-axis. And we'll give this a name. So we'll call this vector v1. It's not an index, it's just a label. v2 and v3 will be the corresponding rotations around the other 2 axes. Okay, so now let's just plug in again g mu nu p mu v nu, with this being v, and we get the equation r squared sine squared theta d by d phi, sorry, d phi by d. Okay, I don't know whether I should call it tau or lambda, because actually right now it's okay to assume that the particle has a mass. If mass was 0, I have to call this d by d lambda, not tau. But then if mass is 0, this looks very strange. But we can take a limit when the mass goes to 0 if we get the final equation. So let's work with an arbitrary mass and arbitrary lambda, except it's affine. We don't commit whether it's time-like or null for now. So d phi by d lambda then. And this quantity we can easily conclude is L by m, where L is the angular momentum. We could call it L1 by m. Okay, so L1 is the angular momentum about Z. Probably this is not an optimal labeling. I should have called this vector V3 and L as L3, but let's not worry about it. So that's one equation. And we interpret this L as the angular momentum in the Z direction, again by analogy with Minkowski spacetime. In fact, the equation is exactly the same in Minkowski spacetime because the capital M factor doesn't enter this equation at all. Okay, good. Then there are two more isometries, and I won't write them in detail, but I'll give them names, V2 and V3. So rotation about the other two axes. And if I summarize all the three rotational isometries as Vi, with I equals 1, 2, 3, then I easily find that the commutator, the Lie bracket, so this is Lie bracket of vector fields. As you know, the Lie bracket of two vector fields should give me a third vector field, and this gives me by cyclic permutation the third vector field. So this equation is satisfied. This is also the algebra of SO3 or SU2, and so it's what we call the rotation algebra in 3 dimensions. So it's as expected. This comes without any i's because these are differential operators, and without i's, differential operators in an inner product are anti-Hermitian. So this is the correct way to write it. Good. Now let's try to do a little more analysis. So let's try to simplify our future analysis. For that, we note that the so we've written several isometries, 3 rotational and 1 time translation, but there's also a discrete isometry which simply says that the coordinates tr, theta, phi go to tr, pi minus theta and phi. This is exchange of north pole and south pole of a sphere. So it's easy to check that nothing changes there. And this under this, and this has fixed points at theta equals pi by 2, which is just the equator. So obviously the equator is fixed under this north-south inversion. And now we can make use of this fact to prove a theorem. So the physics idea is that if I have a sphere and I look at its equator, because of these symmetries, any motion that starts in the equator will stay in the equator. Okay, this is what I want to prove. And once I can prove, which start not in the equator, I meant really in the equator. I did mean in the equator. Will stay in the equator, and now because this is a great circle by the symmetry of the sphere, actually it will be true for any great circle. But in these coordinates, it's easy to prove for the equator. Of course, this picture is a little limited because here I am drawing only the spatial part. Actually it's more than it's not the equator. I think I was right initially. This should be thought of more as a solid thing, and also of course propagating in time. So really it's the equatorial disk where the motion takes place. I mean, it will be outside this maybe. So anyway, this is just a representation of the 2D part of the 4D metric. And let me write the precise equations. So consider a geodesic. It will just simplify our analysis. So some geodesic x mu of lambda. And let's give it some special initial conditions. So there are 2 initial conditions to solve the geodesic equation. So what we are going to choose is that x mu such that x mu at 0 lies in sigma. Sigma is this locus. It's a 3-dimensional space-time locus where theta is frozen to be pi by 2 and tr and phi can vary. So it's a 3 space-time dimensional manifold.
It's a slice.
It's a slice, yes, exactly. And so the initial condition furthermore will fix t, so then it's only an R phi two-dimensional thing, and that's essentially what I meant when I said that there's a like equatorial disk. And so I'm going to assume that x mu at lambda equals 0 lies in sigma, and dx mu by d lambda at lambda equals 0 lies in the tangent space to sigma, which we call T of sigma. So we are starting our particle. Some particle is moving in the field of the Schwarzschild metric, and but its initial condition is that its for coordinate, its initial position is in that hyperplane, and indeed sigma is a hyperplane, and then it also that its initial velocity vector is also in that hyperplane. So the theorem, this is yes. So I haven't stated the theorem yet. Then x mu of lambda lies in sigma for all lambda.
What is meant by tangent space in sigma? Tangent space is about the point.
Yeah, okay. Good. So, yeah, I guess you could say then it's tangent space of sigma restricted to the, so x mu of 0 lies a point in sigma, so it's the tangent space at that point. So it lies in T of, okay, so there is a tangent bundle and we'll be using that soon. But if you want to only call it tangent space, then yes, it should be T at, so let's write it better this way, is the point P labeled by I'm writing it this way, the point P labeled by x mu of 0 is in sigma, and then this lies in T of sigma. Now we are okay. Okay, now the proof is quite simple. This is a fairly obvious theorem. So suppose x mu, suppose the contrary, x mu of some lambda 1, some specific value, does not lie in, is not a point in sigma, then you can use that isometry to show that there's another geodesic. So the isometry, I think I didn't give it a name, which I should have done. In the books they call it capital phi. So we write capital phi of this is that, the image, that's the isometry map. Then if x doesn't lie in sigma, then of course the inversion of x also doesn't lie in sigma. But in that case, both are geodesics with the same initial conditions. Because the initial conditions are invariant under phi. But of course, the geodesic equations have a unique solution if I give fixed initial conditions. So this is a contradiction. I mean, in words, you can just say that if there's an isometry and the initial conditions respect the isometry, then the whole trajectory should respect that isometry. given that the trajectory is obtained by solving a second order equation which is completely determined by those initial conditions. Okay, and so thus we can always take, to study geodesics, we can fix theta equals pi by 2, it saves us some work, and d theta by d lambda is 0. This is the statement that, so we are in that plane. This is the statement that the initial point is in that hyperplane, and this is the statement that its velocity is along the hyperplane. Good. So this actually trivializes the equations for the Killing vectors v2 and v3, so we don't really need to worry about them much anymore. So only v1, the one that we discussed, is relevant. Okay. So now let's talk about the trajectory of a free particle. You might have done this. I think it's generally done in elementary GR courses. So the same trajectory of a free particle is same thing as saying a time-like geodesic. So we have simplified our original setup by appealing to this symmetry. So one convenience, actually we still maybe don't have to say time-like. I'm never sure because this mass of the particle keeps coming up. So so what people do is to define a quantity epsilon which is just minus u dot u, and as you know, for a time-like geodesic, u dot u is normalized to minus 1 automatically, so this is equal to 1. But when we go to the massless case, to the null case, then epsilon will be 0. So we just introduce this, we just call u dot u, instead of saying u dot u is minus 1, we say that it's minus epsilon, and then at the end we'll see if we can set epsilon to 0 to get the null case. Okay. Now we simply need to plug in our various equations. We set theta to be pi by 2, and we look at the equations for theta, for phi and for r, which I already, phi and for t, which I already derived, and we find the following equation: dr by d lambda squared. So we're just going to write out u dot u equals minus epsilon explicitly. Okay, so u dot u will have terms dr by d lambda squared, d theta, d phi by d lambda squared, and dt by d lambda squared. Two of these three things we've already found out using Killing vectors, and so we'll be able to find the dependence of r on lambda, the radial coordinate as it will be. And we find this nice equation, this is equal to e by m whole squared minus 1 minus 2 gm by r times epsilon plus L squared over m squared r squared. At the moment, these equations are not dimensionally consistent because I've set c equals 1. Many books also set g equals 1, which only makes it worse. But we'll put c back just for once, just to see what the equation looks like in physical units. So now now we expand this out. We multiply these two terms with these two terms to get 4 terms, and we get an equation of this form, in which I'm going to put back the units of c. So we get this is equal to some curly, so there are lots of e's in this story. Capital E is the energy, epsilon is just a harmless number which is 1 or 0, and curly E is defined here. It is the original E squared over 2m squared. So then we find that it's equal to this minus V of R. So this is like a standard energy conservation equation in 1D classical mechanics. If you take V of R to the other side, this is R dot squared plus V of R is a constant. So it's just like that. I can only imagine this must have been very thrilling for people who understood GR very early to work out, because it's just an application of what we already know in classical physics, but it gives different answers, and then in these different answers lie the seeds of how general relativity departs from classical physics and gives experimental predictions like precession of perihelion and so on. So it is like, so the equation looks like this, but the potential is not something you would have guessed right away without doing the calculations. So that epsilon, which is 1 or 0, appears divided by 2. Then there is a term minus epsilon gm by r. Then there is a term plus L squared over 2mr squared. This is a familiar centrifugal barrier. And then there is a most unfamiliar term which is generally thought of as the relativistic correction, where you have m squared r cubed, just by multiplying those two factors. And you can see that the ones which have g in them are of course the gravitational terms, but this one is just the Newtonian potential, so no big surprise. But that one is some kind of mix between Newtonian potential, mass of this solution, whatever it is, and angular momentum all coming together. And now we can put C back also, just for fun. I don't think we'll need it later, but let's put it in anyway. So this is C squared. Gm by R has dimensions of velocity squared. So this is C squared. In the next term also we have C squared. And in the last term we have C to the 4th. The last term is actually just the product of these of this with that. And now everything is dimensionally consistent, and the whole this is all dimensionless potential. This is a dimensionless energy, as you can see from that equation. And this is of course ratio dr. This is a coordinate divided by an affine parameter. They have the same dimension, so it's consistent. And this is a wonderful term because it actually dominates as r goes to 0, because it grows as the cube of r. It will win over both the other terms. In usual physics, this is an attractive potential, this is an angular momentum barrier, and so unless the angular momentum is 0, at least we can save the poor particle from slamming into the origin. But with this, nothing can really be saved from going into the origin. Now here I think we can actually set m to 0, because these two terms will disappear because epsilon also goes to 0. But we have to rescale something. I think we rescale lambda, the affine parameter, by m before doing that. And then curly E is also curly E also has 1 by m squared. This will have 1 by m squared. This has 1 by m squared, and this I have a feeling I have made some mistake. Yes, it has 1 by m squared. Good. So we can, let's do it. So can scale lambda to m lambda, then set m to 0, and of course epsilon also equals 0. And then we get the null case. And what do we get in that case? We have a new lambda, which is the scaled one, but we have this d by dr by d lambda squared, and then cancel 1 by m squared factors from those two terms, and then we simply have minus L squared over 2r squared plus gm L squared over r cubed. And of course you can still put the speed of light in if you want. So this is the one which would apply to light, for example, to a light particle in the field of this solution. Yeah, so it's wonderful. I just find it very pretty every time I do it. It's so simple and yet it's so new. Yeah, and so
What about E squared by 2 term?
E squared by 2. Where is E squared by 2?
That curly
Curly E. So that, oh, sorry. I forgot. Yeah, of course. Thank you. E squared by 2. Absolutely. Yeah, it didn't make any sense otherwise. Otherwise, where was the total energy? This is it. Excuse me. Okay, so this is for null. Thank you. Yeah, so it's very satisfying that we got an equation which looks a little different from that, because this thing is, that one is absent, but the other terms actually conform to, I mean, it was possible to scale out m and set it when setting epsilon to 0. So there's generally a diagram drawn which, just to show you that in usual and central force problems we have something like this, where the potential decreases. What is the potential? Sorry, this also goes down again. No? So this is how the angular momentum barrier makes it turn up. But in this case, we have something more like this, where this is that last term. Because of its sign, for the potential, it comes with a negative sign, so it actually turns the potential over down to minus 1. And therefore it changes the structure of some of the solutions. And I'm not going to go over this in any detail, so I'm not going to write down solutions of these equations now. You might have seen them already, but the main purpose of going over all this is that we wanted to prove an important theorem called the Birkhoff theorem. And this requires a little bit of mathematics and using these symmetries. So the theorem hide this joke. I've also hidden one more in a place where I think nobody will find it. Okay. So let's write the theorem and then. So Schwarzschild solution is just one solution, and I think it's 1916. And Birkhoff, I think 7 years later, basically said that with those symmetries, that's the only solution, which is quite a dramatic simplification on what you might expect. So the unique spherically symmetric solution of the vacuum Einstein equation. So vacuum, and of course I should have said cosmological constant also absent, is the one we've written. And the proof goes like this. Well, the proof requires defining a couple of mathematical things, but by now you've gone through a month of mathematics, so you won't mind if I introduce a new concept. So for this concept, So it's a small digression. You know what is, so if P is a point in a manifold, then Tp of M is the tangent space at that point to M at P. And it's a vector space, and unlike the manifold itself, which is not a vector space, and there's a different vector space for every P. So in some sense you shouldn't be able to compare them, but it's actually interesting to take the union of all these Tp of M over all P. So it's a union of sets, and this is called the tangent bundle. So a tangent bundle is just a family of tangent spaces, one at every point of the manifold. And the way you can think of it is that here's the manifold M. Then for any point P, you can draw the bundle as a, just in your mind, you can imagine it as like a fiber over, this is not working. So this is P, so over that point, I erect the whole tangent space of that point, and then I repeat for every P, and so I get something which has the dimensionality of the manifold, double the dimension of the manifold, because this tangent space has dimension D and the manifold has dimension D. So I get a 2D space, a 2 times D, not 2 dimensional, 2D dimensional space. So, and this is Tp of M, and by varying this P all over, I get something which is a 2D dimensional space such that locally it is M cross some T something of M. What I'm trying to say here is that in any small region, I can think of, in a sufficiently small region, I can think of all these tangent spaces, I can sort of identify them. And so the structure of this 2D dimensional manifold is like a tensor product of M with its own tangent space. Okay, but if this point P goes too far away, then this manifold having some topology can mix up these things, and then you get a more complicated space. So this is what the tangent bundle looks like, and this is actually what any fiber bundle looks like, except the special thing is that the tangent bundle is an example of a fiber bundle where the fiber is the tangent space. If you can put some other fiber if you like and make a fiber bundle, but if the fiber is the tangent space, then you get the tangent bundle. And a standard example would be the cylinder, where for the circle, the tangent space at any point is a line. Okay, so the tangent vector to a circle is always a line, and I just put that line vertically and I get a 2D space, which is the cylinder. And the cylinder is trivially R cross S1. So this is the tangent bundle. I don't even know what notation I'm using. Maybe this should be called T of S1. And so it's not just locally, but it's everywhere R cross S1. But you could imagine if S1 was replaced by some complicated, imagine going to one higher dimension and replacing S1 by some Riemann surface with handles or something. Then of course it's not going to be true that this whole bundle is going to be just a copy or product of that with the vertical line, because that vertical line will be forced to vary in all kinds of strange ways as I go over the base. And so in general, the bundle is not a direct product of the base with the tangent space. This is called the base space, this is called the fiber space. It's not in general a direct product, but locally in a small enough region, it is a direct product. That's the idea of a tangent bundle. Okay. So much for tangent bundle. In tangent bundle, we actually took the union of the tangent space over all points. Now we'll generalize it to the following. It's called so what we do is we have M and we consider an R-dimensional linear subspace of TPM. So as I said, TP of M has the same dimensionality as M. But say if that dimensionality is 4, I can consider a 3-dimensional subspace of that tangent space, or 2-dimensional or 1-dimensional. Okay, in general I'm thinking about R being less than the dimension of the manifold. Now, so we take M, we consider an R-dimensional linear subspace of TPM for every point P. And then we varying smoothly with P. This is important. You'll see where this is going in a few minutes. Not that abstract as I'm making it look. So this is the structure I have defined, and then I'll take the union of these subbundles over all P of, so let me call, so let me give a name to this linear subspace. I call it dP of M. Given M, I have dP of M is an R-dimensional linear subspace of the tangent space for every P. So dP is defined for every P, and then it varies smoothly with P, and then I take the union over all points P of dP of M, and I call this D of M. Or maybe I just call it D. I'll just call it D. And this thing goes by the name R-dimensional distribution. So this is a definition on M. So the tangent bundle is a special case where R is D. It's a D-dimensional distribution on M. And in fact, you can think of this as since I'm restricting the tangent space to a linear subspace, you can imagine that I take M and then the fibers, I drop one or two of the dimensions of that fiber. I get a lower dimensional fiber. So the total space of distribution will not be 2D, but D plus R. D for the base and R for the fiber, which is less than D. Okay, good. So this is so it's a smooth subbundle of the tangent bundle. So I hope it's clear. If you understood what the tangent bundle is, then this subbundle is easy enough to of tangent. Okay. So far, so good. Now comes the question. This is a subbundle of the tangent bundle. Could it be the tangent bundle itself of a submanifold of M? Okay. No reason why it should be in general, but certainly if I had a submanifold of M, then it would have its tangent bundle, and that would be a smooth subbundle of the tangent bundle of M. So an example of a distribution certainly would be the tangent bundle of a submanifold. Okay, so let's write that first. E.g., if N is a smooth submanifold of M of dimension R less than D, then T of N is an example of this thing, of an R-dimensional distribution on M. The interesting thing is the converse. Under what conditions is a given distribution, R-dimensional distribution, actually the tangent bundle of a smooth manifold? So, definition, when that is true, so this is clear. If I am given n, then of course I have a distribution. If I am given a distribution, the question will arise whether there is an n, and if there is, then n will be called an integral manifold of that distribution. So, a submanifold n of M is called an integral manifold of the given distribution curly D if the tangent space at any point of n is the same as the distribution at that point. So I told you that the distribution is specified by picking an R-dimensional subspace of the tangent space. This is that subspace, is the union of all of those. But if at every point that thing is just the tangent space of a submanifold, then n is the integral manifold of that distribution. Okay. And if another definition, quite closely related, if such an integral manifold exists everywhere in M, for all P in M, then D is called completely integrable. So a distribution will be completely integrable if it is such that everywhere on M such an integral manifold n exists. Okay, and the last statement is that there is a concept of maximal. So now the last definition is, if this completely integrable so if an integral, if a connected, now we are going to add connected integral manifold of D is not a proper subset of, okay, so there could be different integral manifolds of a given distribution, okay, and if a given one is not a proper subset of any other, then it's called maximal. So that's just a way of picking a unique one. Okay. Now let me explain why we are doing all this. Maybe I should have started by explaining that. What we are trying to do is to use spherical symmetry, which is the only assumption we are given, as well as Einstein's equations, to discover that there is a sphere in the solution. And that sphere will arise as an integral manifold of the associated to the three isometries V1, V2, V3. Okay, since there are three rotational isometries that we are given, you cannot just say so because something has three rotational isometries, therefore its metric has a term r squared d omega squared in it. So that's actually what we are trying to derive. It takes some time. I probably won't even finish it today. Maybe I will. I don't know. But we are aiming at that. And we need one more definition, and then we need a theorem called Frobenius theorem, which basically, one second, will say that given vector fields whose Lie bracket closes, then there is an integral submanifold. Yes?
I didn't understand the part. It is not a proper subset of any other.
Yeah. Actually, I was trying to just in my mind think of an example, and right now I couldn't. But what it's saying is that supposing I find many connected integral manifolds of a given distribution D, then the biggest one is called maximal. Biggest means which contains any others, which is not contained in any other integral manifold. Let's see if I can think of an example by next time. Yeah. Okay, the last definition is also something we have seen before, but we are going to generalize it just a little bit. And this is a slightly more formal definition of foliation. So earlier when we talked about geodesics, we had these kind of diagrams where a manifold was foliated by hypersurfaces. And the idea was that there is some direction, and as I travel in that direction, for every point on this line, there is one hypersurface, not necessarily orthogonal or anything. This is just a label for those hypersurfaces. But then these hypersurfaces are stacked so that they fill either the whole manifold or at least some open set of the manifold, such that every point of the manifold must lie on exactly one of these. That's a foliation. But this is a foliation by hypersurfaces, which I should have said at that time. And today we are going to allow foliations by more general things, which means these guys could be less than d minus 1 dimensional. And what you can imagine, and then I'll write it down in equations, imagine that this is some k dimensional submanifold of M, these leaves of the foliation. Then obviously there is not just one direction which goes across them. There are d minus k such directions. So this generalizes to d minus k dimension. It's not earlier we were thinking these might be a geodesic or some null parameter or something, but now we are breaking the manifold locally into d minus k cross k dimensional thing. Okay, so the foliation then is by k dimensional surfaces, and their co-dimension is d minus k. For hypersurfaces, this was d minus 1, this was 1. So let's write it. So foliation of dimension k since I'm assuming most of you have encountered Schwarzschild solution, you probably can see what all this has to do with it. But anyway, we'll pursue this till we get to the end. On a d-dimensional manifold M, is a collection of disjoint connected immersed. Now I have actually forgotten what immersed means, but an immersion is like embedding, but there are some difference which I can't remember anymore. K-dimensional submanifolds with two properties. And these obviously are called the leaves of the foliation. Such that union of all leaves is equal to n. This is very important. The foliation, if I collect all the leaves of the foliation, I get the whole manifold. It's like taking the leaves of the pages of a book. If I take all the pages of a book, I get the book. That's one. And this, together with the disjointness statement, says that every point of the manifold lies on one and only one leaf. Okay, but there's more. The property is that around every point P in M, there is a smooth chart which, as usual, we write U for its open sets and phi for the homeomorphisms, which give coordinates to those which are associated with some part of Euclidean space. Such that, again, we have a nested such that phi of U is of the form U prime cross U double prime, where one of these is open set in Rk and the other is an open set in Rt minus k. So basically this is like a local factorization property which says that at any point of the manifold, the world around that point looks like leaf one way of k dimensions and something else orthogonal to it of d minus k dimensions. But there's one more requirement. 3. Each leaf of the foliation intersects U. We're still talking of this chart. The open set is U. Either in the empty set, so it doesn't intersect, or in a countable union of k-dimensional slices. I'll draw you a picture and it will become much clearer. Of the form xi equals ci, where I goes from k plus 1 to n. Yeah. So let me just give you an example and you'll see what this is about. Supposing my foliation looks like this, perfectly reasonable foliation. I have not said anybody should be time-like or space-like or anything, so this is a possible foliation. Now, and each of these lines is k-dimensional. Those are the leaves. Okay. So now, if I take my open set like this, the foliation keeps going, of course. So each leaf, so let me pick a leaf, this one, intersects U, this is U. So where does this leaf intersect U? I really wish I had yellow chalk. That is the word, not give me yellow chalk. Okay, so I'm just trying to highlight this particular leaf. The intersection of that particular leaf with U is this part. Right? And that's a single k-dimensional slice. And it can be defined by saying all the coordinates transverse to it are constants. I can just choose coordinates such that this is the level set of those coordinates. Okay. However, if I chose my open set like this and you can't stop me, then the same leaf intersects this one in this part and this part. That's why countable union. In the first example, it was just one slice. In this example, it's two slices. But of course, we might have a very zigzaggy foliation. And then there should be, the foliation can very well be like this. And then if I choose an open set like this, then a particular leaf will just keep intersecting it many times. And we simply want that number of times to be some countable, some integer. Not even if it's not necessarily integer, just countable union. That means it could still be an infinite union, but at least you should be able to list all the entries in that union, count them as 1, 2, 3, 4 up to infinity if needed. Okay, so that's a foliation. So now we actually have a general foliation. And now we can state the key theorem, which will allow us to get to prove Birkhoff's theorem, and actually we'll prove it by constructing the most general spherically symmetric static solution, and we'll find, of course, that it is the Schwarzschild solution. I think this will have to be done next time, but let's do Frobenius theorem. So theorem Frobenius. It brings together all the things that we've discussed above. Let D be a distribution on some manifold. So it's a choice of an r-dimensional subspace of the tangent space at each point, the union of that. Then this theorem gives me the condition when a given distribution is integrable. As I showed you, if there's a submanifold given, then the distribution is integrable and that manifold does the job. But if not, then generic distribution is integrable under the following conditions. D is integrable if and only if for any vector fields that belong to D, any vector fields. So remember, D is a union of tangent spaces, so it has vector fields. So let's call two of them X and Y. The Lie bracket x comma y is also in the distribution. So that's part 1 of the theorem. Part 2 brings in foliations. So this one says that if every vector field in this distribution closes, that is all vector fields in that distribution close under Lie bracket, then the distribution is integral. So far so good. So then there's an integral manifold. But now among those there could be many. So again we should take the maximal one. And so the collection, now here I am not completely sure what all maximal means, but anyway I am writing it as read and I'll clarify next time if needed. Maximal connected integral manifolds of D defines a foliation as defined above. In other words, every maximal connected integral manifold of this distribution D is like a leaf of the foliation. And I think this dimension of the distribution has a dimension R. If you remember, I started by saying R dimensional distribution. So I think seems that it is the same as the K, which is the dimension of the leaves. So this is, I know it's quite abstract, and also I'm probably not going to prove it, but what I'll do is next time I'll stop here, and next time I'll again review what we said, try to see if I can give you a little bit more intuition with some pictures and maybe examples, and then we will define our distribution for the Schwarzschild metric using the vector fields v1, v2, v3, which we already know that they are closed under Lie bracket. Okay, and then we'll argue that it satisfies this property. This property is obvious. Then we'll then we'll say that therefore our spherically symmetric space-time is foliated by the corresponding manifolds, and the submanifolds will be two-dimensional spheres. That is the key point. There'll be, so the whole spherically symmetric space is foliated by two spheres. You could of course skip this whole lecture and say it's obvious that any spherically symmetric space is foliated by two spheres, but that's the proof. That's part of the proof. Rest next time. Once we come to that, we'll be able to write a form of the metric using the foliation, and then there'll only be finite number of functions to fix. Moreover, those functions won't depend on theta and phi, so they'll depend only on r and t. Then we use Einstein equations. Till that time, we don't even use them. It's really a wonder to me that these people who are masters of differential equations, and actually, of course, Birkhoff was a mathematician, and many of the other people were mathematics, physics, some sort of in between, or had in any case very solid mathematical skill. Any questions?